Okay, everyone, good morning. And hopefully you remember last time we discussed OpenFOAM. So basically, we only discussed the brief introduction to OpenFOAM and the file structure of OpenFOAM and how OpenFOAM is organized. Today, we will have a more detailed look at how to use OpenFOAM to run your cases and how to modify OpenFOAM, especially the mesh to generate new mesh for your or modified mesh from the given tutorial cases so that you can do your assignment homework as well as run your other cases which are interesting to you rather than just the specified default cases. And finally, we will discuss how to do the post-processing on ParaView. That is, run ParaView and view the results of our simulation graphically. So you will remember that OpenFOAM consists of three major parts: pre-processing, which has several utilities for pre-processing, such as mesh generation, then the actual solution of our Navier-Stokes equations, which have the solvers, and finally the post-processing, which is, in our case, which will be done by ParaView. So starting off with the mesh generation and conversion. Mesh, as I described last time also briefly, it's just a method to define your problem, to define the physical dimensions of your problem and to represent them in using equations. So in order to represent your physical dimensions using equations, you have to break up your dimensions and you have to break up your actual physical volume into a mesh, which is basically a collection of nodes. As you can see, there can be different types of mesh. Most of the default cases and most of the vast majority of cases involve meshes which have polyhedral cells. And these polyhedral cells have different polygonal faces and they can be of various types. Of course, we will be discussing the most basic of these, a cuboid type of mesh with having our physical volume divided into different cuboid volumes. Now, a mesh with such a general structure in OpenFOAM, it is known as polyMesh. And OpenFOAM provides different cell-shaped tools to manage this conventional mesh for the conventional mesh formats based on a predefined cell-shaped toolbox. Of course, you can also import your different geometry into OpenFOAM as well using other types of software, but we will not go into that. We will be looking at very basic cases and we will be generating the mesh for those cases directly in OpenFOAM. But you should remember that OpenFOAM is also capable of importing mesh from third-party mesh generators. And you can look at the tutorial for that. Now, before the mesh can be solved for, before OpenFOAM can run the solvers or the Navier-Stokes equations can be solved for your mesh, OpenFOAM has a mechanism to validate the mesh. And that mechanism of validating the mesh basically depends on the definition of these different types of variables. Of course, they are self-explanatory, most of them. Basically, your mesh, which I have just told you, is a collection of node points in the space in actual physical volume. It is defined by, of course, different points, the actual vertices of the nodes of your mesh. So basically, point in OpenFOAM is simply a list of vectors describing the vertices. And this is the most basic method of defining your mesh. When you are solving for your customized mesh, you simply have to break up your domain into different points, which can be defined as a list of vertices. Then you have a list of points with face normal vectors defined by the right-hand rule, and these are called faces. Of course, when we have different points such as these 5 points, when we connect these 5 points, the plane between them can be referred to as the face, and the plane between them is defined by the right-hand rule. Meaning, when we are defining the points for faces in OpenFOAM, we will list these points in this right-hand in a clockwise direction. Meaning, if we start from 4, we will list 4, 0, 1, 2, 3. So this is the order in which we will list our points. And how do we know that this is the clockwise direction and not the other one? Because we will be having a cell represented by face. For example, we have a cell, a block. Let's say this is an object and this is our cell. So if we are just talking about this face, so we will have the normal pointing outside. So we will apply our right hand rule like this with the normal pointing outside for this face. If we are defining the vertices for this face, we will not define them such that the normal is pointing into the cell. So for the definition of the face of a cell, we have to list our points. We could list them 2, 3, 4, 0, 1 or 4, 0, 1, 2, 3. All both are correct. But we cannot list them in an anti-clockwise direction such that the normal is pointing into our cell. Okay, then we have internal faces and we have boundary faces. Internal faces and boundary faces simply mean that when we have geometry defined by many different cells, multiple cells, then some of them will be neighbor cells and some of them will be pointing towards the end of our geometry or the end of our domain. We will look at the a diagram defining all of these things, so don't worry about it. So finally, we have the list of the cell, the definition of the cell, and a definition of boundary. Boundary basically in OpenFOAM is simply described by a list of patches or a list of collection of faces. So we can just define in OpenFOAM which faces are representing our boundary. Of course, this will be more clear to you when we are discussing an example. Now, moving on, I will remind you last time we discussed the file structure. I will not go into details, but I will just remind you in OpenFOAM, we had the case directory, which for our case was cavity. Remember, we solved for, we defined a new folder, a new directory in Windows, and we named it cavity. So inside cavity, there were 3 different types of folders. One was named constant, and another was named system, and the last one was named 0. The constant directory has information which remains constant throughout the simulation. And of course, here is where the mesh is also defined, because mesh also generally remains constant throughout our simulation. Once we have defined the mesh at the beginning of our simulation, it remains constant through the various time steps. So, and so the constant directory has a subdirectory named polyMesh, and this subdirectory has these different files. And basically, these are generated automatically. We will I will explain to you how to generate these files automatically by defining just one file. Most of the time, for simple cases, you just need to define one file in OpenFOAM and run your blockMesh blockMesh utility, and it will generate these files automatically. Now, I have just included this here so that you can go through the description on your own later on. I have explained it briefly. If you are interested in reading in more detail, you can go through this slide. I will not be explaining this slide because it is not as important to practically solve our OpenFOAM as other things. Okay, so you can go through it later on. Now, cell description. A cell, as I described earlier, can be a hexahedron box like this, a cuboid, or it can be of several other types as well. And the numbering for the cell can be based on the vertices, the corners, the corner points, or it can be based on face numbering, or it can be based on edge numbering. We will be using this vertex numbering system. There is another very important point. You are generally, when you are starting off with solvers in fluid mechanics, in CFD, you are doing 1D cases and 2D cases. However, in OpenFOAM, all cases are 3D cases. So how do you define a 2D problem or a 1D problem? You still have to define the other dimensions, but you simply have to use a special type of boundary condition for the case of 2D and 1D. For example, if you are solving a problem which is 2D, so you will use an empty patch type boundary condition for the third dimension. For example, if your problem is only defined in X and Y axis, for the Z axis, you will just define a boundary condition named empty. and that will enable the problem to be solved in 2D, but actually the calculations will be performed for 3D. So OpenFOAM always solves problems for 3D, but you can solve problems for 2D or 1D by defining an empty patch type boundary condition. Also, we can also describe our problems as axisymmetric or using the wedge type boundary condition. By the way, whenever you have any difficulty in understanding any of my points, or you have any confusion, you can interrupt me and ask me questions. Moreover, I'm trying to record all of this session, so you will have this session as a video available to you later on to go through my instructions. Now, our example problem is a lid-driven cavity flow problem. Basically, we have a box, a 2D box, and the top boundary of the 2D box, the top wall of the 2D box is moving. It is moving at a velocity of 1 meters per second in this direction. Okay, so this is our example case, and inside, of course, you can understand that because inside we have a fluid, and because of this moving lid, the inside of fluid will be disturbed, and it will have some type of flow taking place inside, and we will visualize that flow in our example case. Of course, laminar flow is assumed, and a uniform mesh will be utilized for our case. And in our case, we have X and Y directions, and the Z direction will be defined by the empty patch type boundary condition. Now, when we are defining a block, we have discussed about defining vertices. Defining vertices are easy. How do you define one point? You simply list its coordinates, coordinates in 3 dimensions. For example, this point is 0, 0, 0. This point is 1, 0, 1, meaning in X direction 1, then in Y direction 0, and then in Z direction 1. So defining a point is easy. We simply define as we are used to of defining vertices or vectors. But how do we define a face? That also I have told you. We define a face by going in the clockwise direction. For example, let's take this face 2. Okay, this is our cell or our example problem, and we are talking about this face 2 of this problem. Now, how do we list the vertices of this cell in OpenFOAM? We use the right-hand rule on this face, and we go in the clockwise direction. So, for example, if we are starting with 0, what will be the list of numbers defining this face? 0, clockwise 4, 1, 3. So this face has been labeled 2, and you can see 0, 4, sorry, this is 7, 7, 3. Okay, so we define this face using the clockwise direction. Okay, let's define face 1, which is at the bottom. So if we are starting with this point is 1. This is 1, 0, 4, 5. So at the bottom, how do we define this face in the clockwise direction? We define this face in the clockwise direction with the outward normal pointing outside the cell. 1, 5, 4, 0. So you can see that this face 1 is defined using 1, 5, 4, 0. Of course, we could have also written 4, 5, 1, 0. That definition would also be correct. Meaning you can start at any point. It's not necessary that you always start at the this point or this point. You can start at any point, but just you have to list in the clockwise direction. So you can list it 1, 5, 4, 0, or you could list it 4, 0, 1, 5, or in any other manner. Okay. So this is how we define faces. But how do we define a block? Because in OpenFOAM, we have to define everything about our mesh to OpenFOAM. So we have learned to define vertices, we have learned to define faces. Now, how do we define a block? A block is simply defined by listing the different vertex points. Okay. For example, this is the definition of the block here, And how are we defining this block? By defining all of these vertices. For example, these are the two planes of our block. We can say that this is the bottom plane and this is the top plane. Okay. So we define by starting from this point, 0, 1, or rather, there is one mistake you should remember. Basically, we have 3 directions. We have so we have 3 dimensions. So our plane can be when we are defining our block, we can take the first plane, xy plane, or we can take the xz plane, or we can take the yz plane. So generally, for OpenFOAM description, we are going to take the xy plane first. Okay. So where is our xy plane here? So our xy plane is here. So when we are defining the planes for our block, we will not take the bottom plane and the top plane because they are not the xy plane, they are xz planes. Which is the xy plane? This rear plane and this front plane. Okay, so we are going to define our block using the rear plane and then the front plane. How do we know that this is the rear plane and this is the front plane? The plane in positive z direction is the front plane. The plane at the back at the start of the coordinate system, this is the rear plane. Okay, because z direction is increasing in this way. This is why this is the front plane and this is the rear plane. So we are going to define our block using the vertices of this plane first. So what are the vertices of this plane? 0, 1, 2, 3. Okay, so the vertices of this plane are 0, 1, 2, 3. So this is the description until this point. And then what do? We move to the other plane. We started off from this point. So 0, 1, 2, 3, and then move to the front plane. 4, 5, 6, 7. Now, in this particular example, our vertices are also labeled in the same order. The numbering is also in the same order. But I have also included other examples in my presentation where the numbering is not in the same order. The numbering can be in any order, but the important thing to realize is that you start off with the rear plane in the XY direction and then move to the front plane. And when moving from the rear plane to the front plane, where do you start on the front plane? Where at the same point where you started on the rear plane. Okay, so this is an actual screenshot from OpenFOAM. This is how you define the list of vertices, and this is a different block. So you can see how this block has been translated into this list of vertices. When you are solving for your homework, you can check. Also, at the top of the OpenFOAM file, you will have you can write a statement convert to meters. Convert to meters statement will enable you to convert all dimensions to your specified value of units. So, for example, if you want to convert to millimeters, you simply write this statement convert to meters space 0.001, and it will convert all of the dimensions into millimeters. So this means that this one will become 0.001. This one will also become 0.001, and so on and so forth. So you can write your code in an easy manner, but the OpenFOAM will convert it automatically. Yeah. Oh, okay. Phase 4 is 0321. Yeah. Phase 4 is okay. Yeah, you're right. Phase 4 is actually they have been switched. This phase 4 is at the back, and this face 5 is at the front. Yeah, so basically in this figure, the front face and the rear face have been switched. You can see that these two are opposite. So yeah, this is a correction. You can notice that face 4 is at the back and face 5 is at the front, but they are in the same plane. Very good observation. But I have included several other examples as well in my presentations. So if you are confused about one example, you can go to another one. For example, this one, I was explaining to you earlier how to define blocks in OpenFOAM. So this is the actual code screenshot which will be used to define the blocks in OpenFOAM. And this file is basically blockMesh Dict file, and this is included in the systems folder. I will show it to you the location in the folder later on. So in this file, if you are defining a block, you use this code. Basically, you write blocks and then define a list. And list has these three things. What are these three things? The first line is explaining that this is a hexahedral cell. Okay, the first line is explaining the shape of the cell, and then describing all the vertex points. Now, in this example, the vertex points are different. Where is the XY direction, XY plane? This is the XY plane. So the vertex point in this example have been described 0, 1, 3, 2 for this XY plane. Okay, so this is plane 1, 0, 1, 3, 2, and then what do? We move to the next plane in the Z direction. So here we move to the next plane, but we started from this point. So we will start describing this plane from this point, 4, 5, 6, 7. So you can see from this figure how this block can be translated into the code. Moreover, you will see that we have another list, 5, 5, 5. This list is basically describing the number of cells in each direction. The first 5 is representing the number of cells in the X direction, then Y direction, then Z direction. So you can see that your final block has 5 cells in each direction. If you change, for example, in the Z direction, if you write 10, then the number of blocks in the Z direction will become 10 in your eventual mesh. So of course, you can play around with these settings later on when you are running your code. And finally, the last line is indicating simple grading, which means that each of the cells are having the same cell ratio. There is no cell expansion or cell distortion going on, but you can also distort these cells as you wish, depending using this simple grading style. Of course, if you want to have more mesh at the beginning, or a finer mesh at the beginning and a coarser mesh at the end, you could use this grading scheme, okay, and use another number rather than 1. This is another example. In this, what's the difference between this example and the last one? That over here we have 5 cells in each direction. Now we have 10 cells in each direction, okay. And if you want to have curves joining your vertices, you can also specify that. For example, so far we have been discussing a block which is defined, where the vertices are joined by straight lines. Okay, these are straight lines, all of these. But we can also define a curved line joining 2 vertices. And if you want to define a curved line joining 2 vertices, we simply specify this list, edges list. And we have different ways of specifying the curve. But if we don't want to specify the curve, then we can simply leave this blank. Leave it blank. Don't put anything. Of course, you have to put edges list, but inside there will be nothing. As I described earlier, that we can have different types of boundaries in OpenFOAM, and here we have a figure which is showing an axisymmetric example, an axisymmetric geometry. So in order to define an axisymmetric geometry, which are the faces that have to be defined as axisymmetric or wedge boundary condition? You will have this face and the other face, okay? you can see this face where there is this wedge patch 1 and the face at the back. Those faces have to be defined as wedge boundary condition faces to have an axisymmetric boundary condition. But the important thing to realize over here is that this face may not be just one face. It may be a collection of faces. Okay, it is not mandatory that this is only one face. There could be 2, 3, or 100 faces here. So this is why we have this term patch being used. We are not using face because there could be many faces, so we are using patch, and we describe the faces, the boundaries with respect to patches. And this is the list of different the basic patch types. Of course, there is a generic patch. Then we have a plane of symmetry described by symmetry plane, and this is the empty boundary condition which we are going to use in our case to define the third direction. The third dimension is empty. Okay, and of course we will need wall boundary condition. The wall boundary condition indicates, as you know, that flow at the wall, the velocity of the fluid at the wall has the same velocity as the wall itself. So if the wall is stationary, the velocity of the fluid at the wall is also stationary. But OpenFOAM takes care of all the details. You just need to specify that this is a wall boundary condition, and OpenFOAM will do all the calculations accordingly. The boundaries have to be specified as well. You have to, when you are describing your mesh, you have to define the vertices, the faces, the blocks, as well as the boundaries to be applied to each of the faces that you have described. Okay, so the pre-processing stage, before you can run your solver, the pre-processing stage, that involves two major steps: defining your mesh itself using faces, blocks, and list of vertices, and then defining the boundaries, the boundary conditions. Okay, the routine order for, or the routine organization for defining a boundary is this: that you first name the boundary patch, give a name to your boundary patch. It could be sides, it could be internal wall, external wall, etc. And then you list the faces in that boundary condition. We will take a look at an actual example. This is just a generic example. We will take a look at an actual example, and that will be more useful for you to understand. Yeah, this is the actual example. Hopefully you can see it at the back. I will not read all of this, but I'll just show you that this is the actual screenshot from the OpenFOAM file. And you can see that at the top of this list, there is the title boundary, which is describing this list, that all the boundary conditions are included here. Then we have several sub lists inside it. And those sub lists have titles, names, moving wall, fixed walls, front and back. And of course, these are the three different types of boundary conditions for our case. The example of a lid driven cavity. There is the moving wall, the top face, then the fixed walls, faces at the two ends. Okay, faces at this end and this end, and of course at the bottom. Okay, so these are the fixed walls. So you can see that fixed walls has three faces. Okay, fixed walls has three faces. Moving wall has just one face. Okay, and front and back, of course, this face and the one into the board. Okay, the rear and the front. So there are two faces in this, and you can see that the type of boundary, whether it is going to be an empty patch type boundary or wall type boundary or axisymmetric boundary, that is also specified here. Okay, moving wall, and then inside it we first describe type wall. This is also type wall. What is the difference between moving wall and fixed wall? Just the velocity of the wall is different. This is fixed, meaning having zero velocity, but both are wall type boundary condition. But this front and back, because we have a 2D problem, this is type empty. Okay, so you can see that the walls are described here. Sorry, the walls are these moving wall and fixed walls, and the front and back wall or the front and back faces are empty. Now, how do you describe the faces? You can see that this is one face 0473. So this is the face again 0473, and again you have to remember that you have to describe it in the using the right hand rule. That using the right hand rule, the normal will point outside the cell. The normal will not point inside the cell. So we have to either use 0473 or use 4730 and so on and so forth. But you have to check for each of the faces that the walls have been the faces have been described using the right hand rule. Otherwise, your case will not run. Yeah, this is another slide describing the same thing. You can go through it in detail later on. Everything that I am explaining to you verbally has also been written for your reference. Okay, this is the boundary file that I talked about. Inside the mesh there is a boundary file, but this file is generated automatically. So whenever you open your case folder and you see a boundary file, you don't need to modify that. So remember this: the boundary conditions are not described in the boundary file. The boundary conditions are described in the previous file which we discussed, which is the blockMesh dictionary. Okay, so even this list is included in the blockMesh dictionary file. So boundary file is not described in the boundary. Boundary conditions are not described in the boundary file. They are described in the same file. So you just need to modify one file. So most of your pre-processing step will involve modifying one file, which is the blockMesh dictionary file. Once you have done this modification, then the boundary file will be generated automatically. And I have included a detail of what the different things mean inside the boundary file. Of course, there are the number of faces and the start face. Start face is simply the face from which OpenFOAM starts numbering that boundary. But you don't need to be concerned about that. So you will see this file once the blockMesh command has been run. And I will just take a moment here to show you the folder. The case folder that we have. Now you will see, I think, I am not sure if you are able to see at the back, so I will just increase the size here. Yeah, so right now when I have not yet run the case, the boundary file is not even there. Okay, boundary file is created once I run the blockMesh command. So before running the blockMesh command, the boundary file will not be generated. So this is what I wanted to ensure that you understand. Now moving on to the next portion where we specify the properties and the solution parameters. Now for the first case, of course, you don't need to modify any of these things, but later on when you want to ensure that your case runs as per your required conditions, you may need to modify them. So I'll just briefly explain that, or rather remind you that this other folder, system folder, has this file control dictionary, and this specifies the run control parameters at the start and end time. Okay, so for for example, you for how many time steps you want to run your case, what should be the start time and end time. Of course, if you are running your case for the first time, the start time will always be 0. But it may be that you have already run your case earlier. and now you want to run for additional time steps. So the earlier time files are already there, and you want to run for the next few time steps. So you specify the start time value as other than 0. So these things can be done in this control dictionary file. Then we have another file called FV schemes, where we describe the finite volume discretization schemes. I remind you, or rather warn you, that don't modify this file before reading the documentation thoroughly. Once you have understood which types of solvers and which type of schemes are there, only then should you attempt to modify this file. But for your case, if you have copied the tutorial correctly from the correct folder, cavity folder, then you don't need to bother about modifying this schemes file for the first time, for the first assignment. The FV solution file contains the different types of equation solvers and algorithm controls and tolerances, etc. Now, for the case folder, before you have run your case, while pre-processing, you will only have this 0 folder. The 0 folder describes the initial boundary conditions and the initial conditions for your case. So later on, once you have solved your case and run your case for several time steps, you will have additional folders, point 1, point 2, and so on and so forth. Those folders will contain the solution. So time directories having 0 folder, the 0 folder contains the initial conditions, and the folders other than the 0 folder contains your solution. And of course, for our case, we have 2 files inside, the velocity and the pressure. Because we are not discussing heat transfer right now, there is no third file. And of course, this velocity the view file has both the x direction velocity and the y direction velocity. This is the slide explaining the runtime parameters that I told you earlier. The start time, the end time, also delta t. Delta t is a very important variable. Basically, delta t is the value of the time step. Okay, what is the time step for which every iteration takes place? Every new iteration takes place. So if you have a very coarse mesh, then delta t can be large. But if you have a fine mesh, meaning if you have a lot of nodes, a lot of vertices in your mesh, then you need to have, but maybe if your case fails, then you need to decrease the value of delta t. Okay, this is another slide explaining the definitions of all of the things that were discussed in the last slide. Moreover, you will notice that some variables have some option, like start from can have an option start time, or write control can have an option runtime. So how do you know which other options are available, right? In place of runtime or in place of start time, what other options can you input into your code? How do you find out? The hard way to find this out is to look up through the documentation and the code of OpenFOAM, which is available on the internet and which can be accessed easily. But as a beginner, this may be sometimes hard to find out. So an easy method is simply to replace the option that you want to find alternates for. For example, I want to find alternates for runtime, or I want to find alternates for the stop at value. What was the stop at value in the last slide? The stop at has end time over here. Okay. So rather than end time, what other options do I have? So you can simply replace a start end time option with some meaningless variable name, just like bananas or some other meaningless variable name XYZ. And what will happen when after doing this, you can save the file and run your case again. Of course, OpenFOAM will give you an error, but inside the error, OpenFOAM will list all the other options that are available. So in order to find out what options are available, you can simply replace that option with a meaningless name, XYZ or bananas or something, and run your case. What will happen? The error given to you will list the different types of options available. So this is an easy way to find out. Like for example, these are the different options given for this variable name. Now moving on, we have the initial boundary, the initial conditions file, U file, and the P file. And what will these files have? These files will specify the dimensions, the units for the velocity, and they will specify the value of the velocity you want to assign. So for example, for our case, the units of the velocity, of course, meters per second, are described in this way. I discussed this last time, how to represent SI units in OpenFOAM. And moreover, this internal field line, what is this indicating? This is indicating that the velocity field is initialized to 0 in all of the domain, meaning when before our case has been run, before the lid at the top starts to move, it is assumed that all of the velocities are 0. Which all velocities? The x direction velocity, y direction velocity, as well as the z direction velocity. So that's why you see 3 zeros, because they are describing the 3 directional velocities, which we usually represent with u, v, and w. So later on, this is the initial condition. Now this is the value of the boundary condition we want to specify. The value of the boundary condition was not specified in the earlier file. The type of boundary condition was specified earlier, but the value is specified here in the initial conditions file in the 0 directory folder. How do we define it? Using this line. Type fixed value, and actual value is uniform 1, 0, 0. What does this mean? That x direction velocity is 1, y direction velocity is 0, z direction velocity is also 0, and so on and so forth. And of course, the moving wall only has this. The fixed walls still has 0, and front back has type empty. Similarly, you can describe for the P file as well, the pressure file. U file was representing all the velocities in our case. The P file is representing all of the pressure in our case. And the pressure, you should remember, is the modified pressure. OpenFOAM uses modified pressure to describe it. So when you are later on converting your results or generating graphical visualizations for your results, remember to divide by density to convert this pressure, this modified pressure, into actual pressure. Okay. So the units of modified pressure are the meters square per second square, and the types of boundary conditions for each of the walls is 0 gradient, meaning basically it is the Newman condition. And I hope you remember from last time where we discussed that what is the Newman condition or the 0 gradient condition, meaning the change in pressure at the wall is 0. The value of pressure at the wall is not 0, but the change in pressure at the wall, the dp dou p by dou n is 0. Now moving on, this is of course the note regarding pressure field, which I told you earlier, that you have to divide by density to find the actual pressure. Now proceeding to post-processing on ParaView. Of course, the first step here. Okay, sure. Okay, then we can take a break and then continue after the break. Thank you.
Then I can give you some work. It's very good. Yeah. But at least I have never seen anyone use Excel to do that. Okay. So Excel probably you can use it to plot the XY plot. Okay. That's fine. But for scientific purpose, that's very difficult. Okay. So there are many different kinds of softwares to do that. You can also use MATLAB as well. Okay. Since we have MATLAB in the computer room as well. And you can also purchase the student version as well. And then you can use GNU plot. GNU plot actually, there are a lot of new, okay, in GNU plot. So then the other option is ParaView. ParaView actually was proposed by the Oakridge, right?
Yeah.
National Oakridge.
Sandia National Laboratory. Sandia National.
Yeah, Sandia National. You know anyone know the Sandia National? No? You know atomic bomb. That's it. Yeah. They are doing that. Okay. But in addition to that, okay, they also do some peaceful research. Okay, like visualize the scientific results. Okay. So after that, they release the version. Okay, and then everyone can use it because they have to announce that they do make some contribution to promise the world peaceful. Okay, so they have to provide a ParaView and no charge. Okay, everyone can use it, and the quality actually is very good. And also they provide a user guide because in the beginning there is no user guide, so you need to try by yourself. That's very ridiculous, but well, it's free, so they don't provide that kind of service. Right. So then after you finish the simulation, you can use ParaView, okay, to visualize the result you just finished. Okay. And in general, there are two variables, two kind of variables, the vectors and also the scalars. So for scalars, you can use in 2D you can use contours, right? So every day you see that in the weather forecast, right? So you can see the patient view on the weather forecast news, right? And then the other one is the vector. So to visualize the vector, of course, the simple way is to use an arrow. Okay, so they can show you the direction and also the magnitude by the length of the arrow, right? Okay, so two ways to visualize those results. And of course, the third one is for fluid mechanics. That's to plot the streamlines. You all know streamlines, right, from the fluid mechanics textbook, right? So according to the streamline definition, you can apply the streamline and you can see the flow pattern. So basically, I think ParaView can finish those missions. Okay. So Ahmed will present the ParaView.
Thank you. Okay, so now we will begin with the ParaView download and installation. I know you have had problems, some of you have had problems downloading and installing OpenFOAM, but ParaView installation is very easy and very straightforward. Just a couple of clicks and you are done. And because there is no virtual machine or any other such complication, the ParaView install succeeds most of the time. So I hope you will not have any problems. This is the link given here for ParaView download. While I'm explaining the website for ParaView, I will also tell you about OpenFOAM, that if you are having any problems, like some of you have had problems downloading and installing OpenFOAM on Windows. So if you are still having problems on Windows with OpenFOAM and you have Windows 10, then you have another option for installing OpenFOAM. And that option is that you go to OpenFOAM website, openfoam.com, go to the downloads section at the top, go to Windows 10 native. There is a Windows binary, which is the type of OpenFOAM installation which I described before. But then there is Windows 10 native. And this installation is different because it does not use any virtual machine. So it is more likely to succeed. And even if you have installed the earlier OpenFOAM, you can also download and install this. It does not contradict with the earlier version. So you can try this on your own. The difference is that it will you'll have to do some command line executions to install it, because it involves these preliminaries. You see here preliminaries. These are very important, that you have to go and download a bash command a bash command line for Windows. And then once you have downloaded the bash command line, then OpenFOAM installation is trivial for Windows 10. but this is only available for Windows 10. So if you are still having problems, maybe you can come to this page and try this type of installation. Now, going back to ParaView, this is the ParaView website, and here we go to the download section, and once we are in the download section, most probably the web page will detect automatically which system you are running, and if it does not, you can select the system from here, and this is the Windows version ParaView. Of course, you see 4 files here. You don't need to be concerned with these 4. I have highlighted in the presentation. You will have to install this .exe file. The other files, these 2 files having MPI option, they are basically for those users who want to run heavy-duty OpenFOAM simulations, which involve using parallel computers, parallelization basically. So for our case, we will just be satisfied with the simple version. And another important thing given here is the documentation section, where we have you have the ParaView guide, the ParaView tutorials, as well as a brief getting started guide. So please go through this documentation, as they will help you in getting up to date with ParaView much more quickly. Okay, so I have highlighted, this is the file that you need to download from the ParaView website. Once you have downloaded it and installed it, it's very easy to install and it's very easy to run. That's why I have not made another installation video, because it is just a couple of clicks and you will get it, hopefully. So now this is the main ParaView window, and whatever case that you run, the geometry of that case and the visualizations will be presented in this window. Your case file and the initial case file, as well as the different types of layers that you add to your case, they will be presented here in this window, in this pipeline browser. Basically, you have imported your case, but you can view it in different manners. You can also, as the professor explained, generate contour plots for it. If you generate a contour plot, that will become another separate layer here. If you generate a vector plot, that will become a separate layer over here. And you can clicking this eye icon, you can disable the view or hide the layers as well. Hide or bring to the 4 different types of layers. So, and this area over here is explaining the different types of properties, and we will go into this into detail in the next few slides. Of course, at the top is the toolbar, because there are so many options. This slide explains what are the different types of options, which are the different types of filters and controls available on the toolbar. Moreover, if you let's just launch ParaView, because I want to show you that if you hover over any icon, the ParaView will also display a brief description of that icon. So even though over here in the toolbar the icons are not given, the descriptions of the icons are not given, but by hovering over different icons, you can have a brief description like this. Okay, so don't be afraid to experiment around with your installation. Going back to our presentation. Okay, these camera controls basically show you different views of your object, of your simulation. These filters, we will discuss them later on, but most of the filters can be accessed using the file menu at the top. You know, these are the icons, but we also have the file menu at the top. So most of the filters can be accessed using the file menu. And of course, this is the main control portion where you open a file, but just by clicking this button and so on and so forth, you can. Yeah, one more thing is this VCR controls. VCR controls basically run through your simulation. For example, you start at time 0, then you pass through point 1, time is equal to 0.1, 0.2, 0.3. You remember, once you have run your case, you will have different directories in your case folder. So this these VCR controls allow you to run through those those time directories. Okay. This is the properties panel, which I explained over here. So this properties panel has different options, and you can select which fields you want to read into the case module. For example, we have two fields for our case: velocity field and pressure field. Velocity field is a vector field, and pressure field is a scalar field. Okay, so they are listed here. If you don't want to import both, then you can skip one of them. Moreover, these are the mesh regions. Most of the time, only using internal mesh is sufficient, because there is most of the time there is nothing useful going on right at the wall or right at the front face or the back face. So you can skip the moving wall, the fixed walls, the front and back faces. You can only import internal mesh, because the fluid flow is actually occurring inside the internal mesh. Okay, if there is no fluid flow within the wall, so you can skip including these in your cases. This is the display panel. The position of the display panel is again in the same location as the properties panel. Okay, over here we have properties, and this is the properties bar, and this is the display bar. Of course, I have not imported my case, that's why it is not expanding. I will show you how to import my case, but once I have imported, then another list of options will open up over here, which are given here in this slide. That the most useful of these options are that, of course, you need to select the field which you are representing. Are you representing the velocity field U or the pressure field P? We can select over here. This is the button to rescale the color chart according to your data range. Okay, so some of the useful buttons or the most frequently used buttons I have highlighted in this slide, but for the others you can experiment on your own, or like I told you earlier, just hover with your mouse over that particular button and a brief description will come forth. And of course, you can also refer to the tutorials. Now we will move to accessing our case from ParaView. Now, before we access our case, we of course need to run our case. So during the break, I took the liberty of running the case, and you will remember I told you last time how to run your cases, especially the tutorial case of cavity flow. There are two commands to be run. Of course, you need to import the tutorials folder first. But once you have imported the tutorials folder, you need to run two commands. One is the blockMesh command over here. And does anyone remember the other command? Do you remember the command to run the solver? This is the command to run the mesh generator. But does anyone know the command to run the solver? IcoFoam, the one we are using. Of course, there are other solvers as well. One of them is PiezoFoam. We are using the solver IcoFoam.
PiezoFoam is for cover flow generation. IcoFoam is for linear case.
Yeah, because we are running a simplistic incompressible laminar flow case. That's why. Now, of course, this is the command that I ran for running the solver. And after the solution is complete, I get this command line back again over here. Now, what does this mean? This means that the necessary case files have been generated in the case folder. So you can see that this is the case folder, cavity. Okay, this is the cavity, and these are the time directories which have the solutions for our case. And if we go into the constant directory, you see that there is now a new directory, polyMesh, and this polyMesh directory has all the boundary and faces and neighbor files, which I explained to you that they will be generated automatically, and they have been generated. Now, in order to import this case into OpenFOAM, because we are running on Windows, we have to do something manually, and that is we have to make a new file over here. Okay, so just right click and go into the file settings and just select any file. I'll select a text document, and now I will just name this file cavity.foam. Okay, this is very important. You will notice that what was the file name earlier. Usually whenever we create a file, it's given an extension at the end. Like when you create a file, it's given a text file, it's given a .txt extension, or if it is a Word file, it will be given a .doc extension. These extensions usually do not appear over here. How do you enable them? You go to the menu and you go to the view menu, and over here you enable these extensions by clicking on file name extensions. Okay, if I click on file name extensions, you see that extension appears over here. Why do we need this option? Because we have to change this extension. We have to remove this .txt extension and in fact give one extension of our own called .foam. Okay, so once we have created cavity.foam, it will give a warning. Just click yes. Now we have a new file. Of course, it's a blank file, but the important thing is that it is a file with an extension .foam. Now the location of this file is also important. Where do I create this file? I create this file in the root of my case folder. Okay, cavity, and over here I create the cavity.foam. I do not create it inside system or inside constant or inside one of the time directory. It is just created right at the root. So now I can import this file into ParaView by clicking the open icon and going to the file path. I should know the file path for my case. Okay, and here is the cavity.foam. So now cavity.foam has been imported, but we need to do some further steps. What? As I told you earlier, we have to select the mesh regions. I am only selecting internal mesh. I know that this may not be visible from the back, but these screenshots are included in the slides as well. So you can go back to them later on. I am clicking the internal mesh over here and then clicking apply. Okay, so now my mesh has been, my case has been imported, and what do you think is displayed over here? These are contours, and contours can be displayed by using the surface option over here, by selecting the surface option in the top toolbar, or by selecting the surface option over here, representation surface. And what is being represented? The coloring is according to P, which is the pressure. Of course, I can change the coloring by using a different preset. I can choose a preset of my liking. Let's use rainbow to make it more bright colored. Now, if you try to understand this physically, it makes sense, because what was our problem? Our problem is a cavity where the top lid is moving. Okay, so when the top lid is moving in one direction, what will happen? The pressure at the corners of this box will change. Okay, and how will the change occur? Of course, the pressure at the end of this box, this will increase, this one will decrease, because the plate is moving in this direction, flow is getting diverted into this direction. So this is what is happening, and I am now explaining to you the different types of options you can use. When you click this coloring menu, a list of different variables comes out, and within them there is another one. Of course, U will be there, which is the velocity. You can have view the velocity contours as well. And P, there are two P's. There is this P with a small dot, and then there is a P with a box. What's the difference between them? That you would remember our region. Our region is divided into a mesh. It is divided into let's just view this mesh using the wireframe option. Okay, I selected, rather than surface, I selected the wireframe option, and this has given me this view. So what this is just to remind you that our region is consisting of this mesh, and it has many cells. Okay, in each of these directions there are different number of cells. So our solver calculates one value for pressure in each of these cells. So within a cell, the value of pressure should not change. Okay, so if we want to have constant values of pressure in each of these cells, like within the whole cell, one value of pressure, within another, within one cell, one value of pressure, within another cell, another value of pressure. If we want to have representation in this fashion, then what do we want to do? We have to select surface here, and then select P with a box or P with a cell icon over here. What will this do? This will show the single values of pressure in each of these cells, and same for the velocity as well. Okay, you can see that now the display is sort of distorted because each cell has single values. So what is the other one doing? What is this option doing? This option is basically interpolating between your results. It is just interpolating the pressure between the cells and giving you a constant continuous gradient. So it is not solving further. It is just taking your existing results and showing an interpolation of those results. So you should remember, because when we are viewing this view, we tend to forget that our object is consisting of individual discrete cells. We think that it's continuous. It's not continuous. Actually, the values are given by the actual values are given by the other view. So just to remind you, I'm elaborating this point. Now moving on. Of course, all of this I have described in the slide as well, that how you have to create a cavity.foam file in your case folder and open this file from within ParaView. And the process to open this file from ParaView is also explained here. Okay. Now, of course, the case mesh can also be viewed, and different options for viewing the case mesh are also described, which I have already explained to you. The ISO surface and contour plots, how to switch between different variables, and how to switch between how to rescale the data points. These are described in this slide. I have already done all of this with you. Of course, the rescale button. I think I forgot to press the rescale button here. Okay. Next, we will generate vector plots. I'll only show you how to generate vector plots. The method to generate streamlines are very similar, but I have left that as an exercise for you. I will show you how to generate vector plots now. Of course, they are described in this slide as well. So first we create a slice. What does this mean? It means that you see our problem, it is a block. Okay, it is a 3D block. And why is it a 3D block even though we have a 2D problem? Because I explained to you earlier, OpenFOAM describes everything as 3D, even 2D things. But the solution has been carried out in a 2D manner. So what does this mean? That the same data points are on each of the XY planes. The front plane of this block or the rear plane of this block, all of them have the same values. The values are not changing in the Z direction because it is a 2D result. So now I will generate a slice through this. Okay, so this is the button or the icon for generating a slice, and the slice can be generated in different directions. I will generate a slice with a Z normal. So this will give me, you can see, a single plane. Okay. And after selecting every option, I have to click apply. Okay, so I have done that. I have clicked apply. Now the next step, as described in the slide as well, is that I go to filters, go to alphabetical, and then choose cell centers. Okay, because the actual values are given on the cell centers. The rest of the values are interpolated values. So I get this screen over here again. What I need to do is click apply. Then while cell centers is selected, again we go to filters, go to alphabetical. The alphabetical menu of filters basically lists all of the filters in an alphabetical manner. And here I select glyph. Okay, in order to do a vector plot, I select glyph menu from there, from this screen. And once the glyphs are available, I choose a scaling factor, a scaling mode, and a scaling factor. The screen over here is very small, and basically I have to ensure that in cell centers we have coloring of hue over here. So that is what was missed in the first attempt. I choose a scale factor of 0.005 and then click apply, and then view my vector plot. However, it is not colored according to my liking because the coloring is not according to the glyph vector. So I choose the glyph vector. Then I choose the coloring scheme. And then I remove the background because the background is interfering with our view. And you can see that this is the vector plot for our case. And if you analyze it, it makes perfect sense because the top lid is moving in this direction. So we will have a flow occurring in this manner as a rotating flow. And now we return to our slide. Basically, this is where the tutorial portion ends. Now you will have to, I will just briefly describe in a few slides how to do your homework. Okay, so you remember your homework professor gave you last time, which is due next week, and the geometry for that homework I have described in this slide. Of course, overall case appears to be the same because the top lid is moving, the rest of the walls are fixed. So far it appears to be a very simple case. What's the difference? The difference is that in the middle there is a block, and which this block you have to treat as having fixed walls on all sides. And I have taken the dimensions of the block to be half the dimension of the whole length. Now, in order to import this block into OpenFOAM, we have to create blocks of our own in OpenFOAM. And those blocks each have to have a portion with fluid. We cannot have a block where there is no fluid or no flow taking place. So, although at first instant it may appear to be more easy to just make this large block and have another block inside, but the block inside will not have any flow inside it, and there is no need for any mesh inside this block because there is no flow taking place over here. So we have to identify the node points where flow will be taking place, and in order to do that, we'll have to divide our object into other blocks, and those blocks are listed here. I have numbered the blocks 1, 2, 3 until 8. But remember that each of these blocks is in 3D because OpenFOAM will not take 2D geometry. It will always have to take, you will always have to specify 3D geometry. So basically each of these blocks is in 3 dimensions. So it is a cuboid. Now, in order to describe this cuboid in OpenFOAM, what do we do? Basically, we have to recall from the first few slides. We have to define the vertices. We have to define the vertices. All of these points, all of these points, all of the points on the rear face, all of the points on the front face, all of the points in the middle. All of those vertices have to be described in OpenFOAM. In the same manner as we described for the earlier case. Just what's the difference? The difference is that the number of points are more because there are points here in the middle as well, which were not there earlier. So the next step, what's the next step? We have to describe the points and we have to describe the faces. Remember, I told in the beginning of the lecture that OpenFOAM mesh generation is described in terms of points, faces, and blocks. So we have to describe the vertices of all the points. We have to describe the faces for each of the blocks. And then only can we move on to making the individual blocks. So after describing the points, the next step will be to make the faces, all of the faces. So these are all the real faces for the blocks, which I have numbered. You can see the numbers over here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 until 15. Okay, so there are 16 vertices on the rear block. Why do we need numbering? Because later on, when we are defining the block, we have to use this numbering. We have to use the numbering of the vertices. And this is the numbering on the front face. Okay, so you can see that wherever the numbering ends over here, it ends on 15. and it starts from 16 again, okay, until 31. So there are total 32 points. But why do we have 31? Because we started from 0. Because in most programming languages, with the exception of MATLAB and very few, the numbering is always started from 0. Yeah? So because OpenFOAM is written in C++, the numbering will be from 0. So I've also described in this figure, in this slide, the numbering for each of the blocks. So your task is made much easier because now you have the numbers of each of the blocks on this slide. So when you recall again, what are the steps in describing your geometry? First, you have to describe all the points. Then you have to describe the faces, and then you have to use the faces to describe the blocks. So now the next step is, of course, using the faces to describe the blocks, and all of the blocks have been separated. So you know that this block will have this face sharing with this block. So this face will be defined in the definition of this block, and it will be defined in the definition of this block as well. Okay, so they are the same, but the vertex points will be the same. So you can see the vertex points are the same. The numbering of the vertex points are the same, and so on and so. Of course, these two will not share because there is a gap in between. Moreover, when you are specifying the boundary conditions, you have to describe a fixed wall on this side, this side, this side. Of course, it's understood, but you also have to describe a fixed wall on the inner side. Okay, on these sides. So this is also something that you should remember when defining the boundaries conditions file. Now I will go to the file, the actual file that you have to modify. Oops. Yeah, this is the blockMesh dictionary that you have to modify. You can use any editor. I am using Notepad++. You can also use simple Notepad to edit these files. And so this is the file for the simple cavity block. So there are only 8 points here described here, but in our case there will be 32. Moreover, how do we know which vertex point? On the figure I have labeled the vertex points 1, 2, 3, 0, 1, 2, 3, 4 until 32, until 31. But there are no labels here. So how do we know the labels? Basically, the ordering is the label itself. Okay, so the first vertex point is vertex point 0. The second one is 1. The third one is 2, and so on and so forth. Okay, so the number in which these vertices are listed, the order in which these vertices are listed, they are indicating the numbering. I don't have to specify a number next to it. Okay, so this is the vertex point 7. This is the vertex point 0, 1, 2, 3, 4, and so on and so forth. So the order in which you specify the vertices, they will indicate the numbering, and that numbering has to be used when you define the blocks. Okay, when you are defining the blocks. Of course, over here there was only one block. Now we have 8 blocks. So here we had to define only one block. But in our case, we will have 8 blocks. Walls. Of course, the walls, these are the boundary conditions described in the boundary file, and in the boundary list. In the boundary list, we have to list the faces. Okay, we have to list the faces. So this is the moving wall face. Now, how many moving wall faces do we have? Now we have 1, 2, and 3 moving wall faces. Moreover, how do we define these faces in that place? In place of 3, 7, 6, 2, how do we define? For this case, for this block, we define the face as 12 using the right hand rule, 12, 28, 29, 13. Okay, so the face for this block to be described in the moving wall list 12, 28, 29, 13, or we can also say 28, 29, 13, 12. We have to specify them in a clockwise manner using the right hand rule with the normal pointing outside the block. Similarly, for this case, what will be the list of vertices in the face? 13, 29, 30, 14. Similarly here. So rather than having one, we will have 3 over here. Rather than having one fixed wall, how many fixed walls do we have now? 1, 2, 3, and 6. Then bottom 7, 8, 9. Okay. Insides 10, 11, 12, 13. Okay. You see these sides, bottom sides, all of them are fixed, and the insides as well. So all of these faces have to be defined. How would you define this face in the fixed wall case? You have to point the normal outside the cell. We cannot describe it like this. We have to describe it like this. So 1, 2, 18, 17. Okay. 1, 2, 18, 17, and so on and so forth. The last of these boundary conditions have the front and back. Now, in our earlier simple case, there are only 2 faces on the front and 2 faces at the back. Now, how many do we have? 8 on the front and 8 at the back. Okay, 8 on the front, 8 at the back, and each of them have to be described how? Using the right hand rule. 17, 18, 22, 21. So this is how you will modify your this blockMesh dictionary file. And once you have done this, you will just run blockMesh command again. And if your blockMesh has been modified correctly, the command will run successfully. Otherwise, you will have to troubleshoot. You will have to find out your error. I also listed the vertices in this file, the boundaries in this file, just to give you an idea. And finally, we have the appendix. Appendix has basically the routine commands that you are likely to use while using OpenFOAM, because OpenFOAM is used in a terminal, and the terminal is imported from Linux. So almost all of these commands are Linux commands. If you use Linux or have used Linux, you already know. Otherwise, you can just learn them. They are very easy, which are and the descriptions are also given, so I don't need to describe anything. Just remember that whenever you are using this rn command, be very, very careful. Rather, I suggest that you don't use the rn command. You can go to Windows Explorer and do drag and drop or delete manually, because rn command using this r option is will remove whatever directory you specify without asking you for a prompt, without confirming from you that do you want to remove this file. No, it will just remove it, and you will be done with that file. So by mistake, if you select a top level folder, all of those directories will be removed. So don't be very careful with this command, or don't use it. Similarly, the move file command will also change the name. So if you change the name and don't remember it later on, you will lose your file. Okay. Of course, in OpenFOAM, for most of the commands, you can use this help option. Like when you want to run the blockMesh command, you simply type blockMesh and click enter. But if you want to have a brief help menu, either you can refer to tutorials, or even on the command line, you can write this help option. These are the references, and that's all. Thank you for listening. If you have any questions, you are welcome to ask me.
Okay, so in a first homework, you should use that problem, okay, and then you should build a model, and the model of course include the mesh and also the definition of boundary condition, okay, and then you should use the icophone to simulate. Then finally you should use ParaView, okay, to visualize the result, right? Okay, so perhaps you should consider the Nolan number, so such as like 100, okay, and through the definition of viscosity, you can define the different flows like a different Reynolds number, okay. So you can fix the geometry and just change the viscosity. Then you can define a flow at the Reynolds number 100. Okay. So in when you submit your homework one, you should show the some results. Of course, in the beginning, we will just ask you to show some like the pressure contours. Okay, and then also you should visualize the velocity vector. Okay. So, and of course you can consider the real 3D as well if you want to explain what is that? Right now in Z direction you have only one, right? One layer, right? You can use more layers. That means from like consider a cube. Okay. But of course, in the beginning, you can just consider just a 2D flow with a square block inside. Okay. And so I'm not sure how long will it take, but basically you can use about 1 week to since next week is also a midterm exam as well, so you can use next week to finish the homework one. Okay, and then probably we should create a submission.
Okay.
In the Moodle. Do you know how to do that? Right?
Yeah,
okay. Yeah. So you can submit your PDF file. Okay. Don't print out your results. Okay. Submit your PDF file to Moodle. Okay. Then we can check out your results. Is that clear? It should be very clear because no question. All right. So if you have any question or you want to extend, because actually for you probably, for us maybe it's not so difficult, but for you, it's first time for you to use the OpenFOAM, and maybe you will encounter some problem or difficulty. But remember that that's also kind of training. Okay. As a scientist and engineer, you must know how to solve your problem or difficulty. Okay. And fortunately, there are many documentation in the website of OpenFOAM and also the forum as well. I should also suggest you to browse the website called CFD Online. There's a forum relevant to OpenFOAM, so you can also propose your question to the forum in CFD Online. And of course, that's we need to propose. This is a very good website. I mean, for you to search for some resources and also propose questions. And even you can find a job in the CFD industry as well. Right? Could you?
Yeah.
Could you search for this?
Yeah.
So if we cannot answer a question, you can also, post a message in the forum of CFD Online, and then you can someone will sometimes someone will ask reply you, tell you the answer.
CFD-online.
Yes. This is CFD Online. Okay, and there are many forums. If you go to that one. So there are different kind of forums, and remember this OpenFOAM. So you can see even the answers, okay? Here, it's OpenFOAM forum. You can also, in future, if you want to continue to use this, you can also use this forum to get some answer or find some examples in this forum. Any question? How to save your PDF file? No, you should use Word to to edit your homework. Okay, and then you're going to catch the image from ParaView to Word, and of course you need to explain, use some text. Okay, explain your results. Okay, and then use the Word to generate PDF file. Right. Okay. Okay. You cannot just use ParaView to generate an image and then send the image to me. Okay, and without any explain. Okay, that's not homework. Okay, homework should also describe how you get the results, and also your model as well. Right. Any question? We don't have midterm exam. We have only homework. Okay, I'm thinking about it. Probably, we will have an oral exam. Okay, so you don't need to write the exam for this. Okay, so I will ask you some questions. I will know how many percent of content in the lecture you understand. Okay.
That's mean that's mean we have to yeah.
Yes. The content you know. Yeah. Okay. So that should be quite easy. But for me, it's also very easy to know if you understand my lecture notes or not. Okay, it's quite important. It's very different from the conventional homework because in the conventional way you need to write homework and from the problems in the textbook, right?